All right, we're rolling. I understand there's a question, Master Set 2.
Master set 2. On number 5, I don't remember you going over the sketch. Some of the following vectors. I got help from the tutor, but
Oh,
did you go
adding
over
vectors?
that?
Yeah.
Because I don't remember that from the lecture.
Okay, so Master says chapter 2,
What was due today, but he changed it to Thursday.
to the 5th.
Yeah.
Okay, and then
And they
where do you
have,
find the homework?
and they, if you go to tutoring. and
All right, so when adding vectors,
They only have tutoring and
so I'm going to define, instead of writing out to the right, I'm just use I hat to indicate that way. I'm going to indicate let j hat mean that way. So if I have 3 I hat plus 4 j hat, that means I go 3 to the right and 4 up, 3, whatever the units happen to be. So 3 this way, 4 that way. And where I end up relative to where I started is a vector from where it is. That would be the resultant, would be, excuse me, would be this vector right here. Now, this is size 3 and that is size 4, the Pythagorean theorem tells me that's going to be a 5. That's a right angle, because that is a right angle. This angle right here is not something I'm expecting you to find, but if you vector it, you should, I would hope, be able to find it, but that would be somewhere around a 53-degree angle. So this is an expression of a vector in rectangular form. In polar form, I would express the same thing as 5 and 53 degrees. These are just 2 forms of expressing this one vector. Now, if you notice, when I added these 2 vectors, I started at a certain point, I went over a certain amount, and then I went up. So right here, at that intersection right there, I have the head of one vector touching the tail of the other. And students, for the most part, have less trouble with it here than if I put them at a strange angle. But that same rule applies if I have a vector going like this and like that, and I wanted to add them. Well, I can treat it as I'm moving. I go a certain amount this way, and then I have a new point right here, and then I travel in that direction. That vector and that vector should be in the same direction, same size. So my resultant is a vector from where I begin to where I end. So that blue vector right there is the answer. That is the resultant.
Okay.
So adding them graphically, so I can just make it more generic. If I had a vector going like this and a vector like that, we'll call that A, B, and C. If I wanted to add them, the order in which I add them does not matter. In math speak, that means the commutative property addition holds. I pick a vector, I draw it down. It needs to be same magnitude, same direction. That's intended to be A. Now I'm here. Draw one of my other vectors. I tend to go in order, but I don't have to. B, I'm going up at that angle right there, that amount. So A, B, and then C, I'm now here. I add C to it. So I've added the 3 vectors using the head to tail method. This is the graphic way of adding vectors. And the resultant, the sum, is a vector from where I begin to where I end. In other words, if I had to give just one direction about how, if these were all directions that you're walking, and I had to give just one direction, well, you would go at that angle, that far. So this right here is my result.
Okay.
Did that answer your question?
Yeah.
Okay.
I might have missed it, but I didn't remember going over it.
Yeah, there's should be a video,
In the book?
there might be one. Now, what Hewitt does it slightly differently when you're adding two vectors. He does what he refers to as the parallelogram method. If adding two vectors, so right here, I was adding these two vectors, all I did was I moved this vector to here, and I added. What he does works fine if you're dealing with two vectors, is he basically creates the parallelogram, and the resultant is that. And that's fine, but if you're dealing with adding more than two vectors that way, it becomes a mess. Perhaps a more creative student could have a better way of showing it, but whenever I try to do three using the parallelogram method, it looks like graphic
And you
gibberish.
said there's videos on here to show?
I
us?
should have created a video about adding vectors graphically. It might be the one where part of it is 110 version, and then I give a limit of, up to, it's 110 up to this point, and then after that, it's 151, 251.
And
Yes,
then,
John?
the head to tail method, and then the difference, like, what we find at the end, would be like the whole answer? Like.
The whole answer is what I have drawn here.
Yeah, so, but when we do the method, and then when we have the last one, what we find at the end would be like, that whole thing would be our answer, is what I'm saying.
When you say that whole thing, so in this case right here, you're referring to the green lines and the black lines?
No, just the black.
Just, yeah, the black line is the whole answer.
Okay, so, but we would just need to write that for our answer.
Yes.
Okay.
I mean, and it could be like this, I mean, you don't have to erase all that and just draw this one line.
Wants you
In the book, right?
to, yeah, look
And
at and do.
what I-
because it
what I
will
don't
prepare
want
you for the quiz on
Is just the green lines and don't draw the black lines.
Yeah.
Because that would be as if I said, what's 1 plus 2, and you wrote 1 plus 2, it equals 1 plus 2.
If you can move back here.
Yeah, it's a true statement, but you have to really answer the question. Jason?
I know you said this earlier, but I'm having trouble believing, that if you start with angle C, for example, it will be the same line.
Now, the way I draw it, it might not, but if I would do it precisely, it would,
Okay,
but
you're right.
let's see how close I get.
Okay.
So, I'm gonna start with C.
But it's solely to purchase.
So from here,
Like, I'm gonna meet with the teacher tomorrow and do those.
all right, that's supposed to be C.
Yeah.
A or B next?
Meet with the tutor, he's gonna be there.
Okay, all right, so A.
I'm just gonna come in and define it. Do close homework, so. Cause the more I practice, the more
A.
I understand.
And then B,
Cause see, I didn't remember this at all, and I was like, looking at this, I do this picture, so I thought that's what he wanted. And then I went to the tutor and he said,
that's
nope,
B,
that's not
and
what
so
he
my
wants.
resultant,
This right here,
you can see it now?
Yeah, I can see that.
the master taking also stuff for application.
Yeah,
It has nothing.
It's not perfect, but if you're adding graphically, especially on the master set,
No, that's
there's
just
close
heavy.
enough. I mean, when I look at it, I can go, all right, the resultant's pointing in the right direction. There is a resultant. They clearly know what they were doing about. I would have drawn A a little bit differently than they did, but yeah, close enough.
Yeah.
And then for the equation, how did you get the answer that it equals to?
That it,
The
How did-
5.
how did I get that it was 5? All right, when I'm doing this notation with using directions with I hat and J hat, they are perpendicular to each other. So when I draw my head to tail here, I'm creating a right angle. My resultant is basically the hypotenuse of a right triangle. I know that if I have a right triangle, that's like A, B, and C, I know that A squared plus B squared equals C squared. The Pythagorean theorem. And I just assume everybody is comfortable with it, because in the past, no one has said they weren't. But this is, if something's a right triangle, this is true. If this is true, it's a right triangle, where C is always gonna be the long side. So in this case over here, I had 3 squared plus 4 squared is equal to C squared. This happens to be 25.
I don't know where his
9 plus 16 is 25. And so C is equal to 5. That's how I knew it was 5.
Yeah, it's down
I picked 3 and 4
to the right.
because it was a simple one. That's 53 degrees, that requires trig, which is beyond the scope of the course, so just. Generally, in a problem like this, if I wanted you to give me more detail, I might say, what's the magnitude of the resultant? I would not ask for the angle unless the angle were something nice, like 45 degrees or 0 degrees or 90 degrees, or something like that.
So if we did have to put the angle in the equation, you would tell us.
Yes.
Okay.
Other questions?
I have another question.
Any other questions on this or Genesis?
Is that a TR or 1R?
This right here?
Yes, for the resultant.
When writing, indicating something as a vector, the most common thing that I do is to put the vector symbol over it, to say it's a vector. For whatever reason, for whatever trauma happened in my childhood, when I draw resultant, I use what I call the double print R. This is just another way of expressing vectors. I could have expressed A as like that, B. So double print also works. It's just that, I don't know why I do that, but that's just another way of representing a vector.
What if, okay. So we
You don't have to, you could just do R with a vector symbol over it, or,
Okay.
but, okay. Yes, Christina?
If we would have answered in form of degrees, would that still be okay? Like, since you figured out the right angle and just do the difference of that whole measurement, the triangle. So since it's 53 degrees plus 90 equals up to, can we answer it in that way?
Oh, what that angle is?
Yes.
Yeah, I don't think I've done that for 110, but yeah, the sum of those three angles should be 180 degrees.
Yeah.
So those could add up to 90, since that's 90 right there.
Okay.
So that's a 37 degree angle.
Okay. But we can't answer it like that on the test. We have to do it like how you have it there, where it's C equals 2.
That?
Yeah.
It depends on the question. If I just said, I have two vectors, one is 3 units to the right and one is 4 units up. You could get away with, the final vector is, I'm gonna say I hats that way, j hats that way, 3i plus 4j is the answer. That is a legitimate way of expressing a vector. If I said, what is the magnitude of that vector, you would use Pythagorean theorem, it'd be 5. I would not, in 110, say, at what angle is this vector pointing?
Okay.
That is, sorry, flashing back. There was an adjunct professor or an instructor years ago who was teaching 110 students tricks so that they could do that. I will not torture you.
Thank you.
Robert I'll torture, but no one else.
You promised me no trick. Promise.
Okay, so I guess I won't torture him with that.
So the whole equation would be our answer. We wouldn't have to put the, like the,
If I just said, what is the vector, this, you could answer it like this.
okay.
Other questions on this?
I'm sorry, can you just go over one more time, like how you got everything? Like, I'm just confused completely.
Yeah. One out. Sorry, need some work here. Okay, so the question is how to add vectors graphically. That's where we start. if you think about a vector, regardless of the connotation, if I have a 3 Newton force, I have a box with 3 Newton force pushing that way and a 4 Newton force pushing that way. And I said, what's the total force acting on the box? Force is a vector, there's a magnitude and a direction. One method of doing that is I could just say, well, I don't want to feel like writing out to the right, so I'm just going to say I hat. The hat indicates it's a directional vector. I'm going to say I hat's that way, j hat's that way. And so the total force acting on this would be 3 newtons I hat plus 4 newtons j hat. And you could be done. If I said I hat was positive that way, then this would become negative. If I said, what is the magnitude of the total force acting on it? Well, I have 2 vectors here that I would add together. And this sort of sounds like a contradiction because this is the notation for a vector, but it's also the sum of 2 vectors. The parts are these 2 perpendicular things.
So if you ask the vector of the box, that's the answer we would give.
Yeah. If I ask what's the total force, that is, you can get there and stop, be done. You can make it far more complicated if you wish. And if this is like a typical class, at least one person in here will. I guess you're volunteering. So. Now, if I ask what is the magnitude of the total force, well, I have to go 1 step further. I have 3 newtons going to the right, plus 4 newtons going up. So the way that you add vectors graphically is to do what's head to tail. You can treat it like I go, think about walking. I walk 3 meters to the right, I walk 4 meters, let's do 3 meters east, 4 meters north. Where am I relative to where I started? Well, if I started here and ended here, then my resultant is there. And if I said, what is the magnitude of the total force? I'm asking for the magnitude of R. In previous math terms, I'm asking what is the hypotenuse? So if that's a 3 and a 4, using Pythagorean theorem, it turns out that is going to be 5 newtons.
And how did you get 5?
All right, if I have a right triangle, then I know if I take the square of the 2 smaller sides, I got 3 sides here, the hypotenuse is the long one. I take the square of the 2 smaller sides and add them together. So that's 9 plus 16, or 25. That's going to be equal to the long side squared. Take the square root, get 5. Physicists like 3, 4, 5 triangles.
Yeah.
5, 12, 13 also works. It's known as a Pythagorean triplet. So what I was doing was leading towards when you're adding vectors, head to tail is the way that you add vectors graphically. So we can take that idea of adding, I start at some place at the tail, I go to the head of that vector, right now that's the tail of the second vector, and I go there, and I just keep going until I've run out of vectors to add. So in a problem where I gave you multiple vectors, vector A, vector B, and vector C. If I added those together graphically, I start with one of them. Doesn't matter which one. I start with one. I tend to start with one, and then I just move either clockwise or counterclockwise, but that's just the way I'm doing it. I'm going to start with one. I pick a starting point, and I just draw it. So that should be the same direction and the same magnitude as A. And now I have a new starting point. I'm now here. I draw another vector. I'm going to take B. B, that's A. Now I'm here. And now I'll take my next vector. Made it slightly too long. So a little bit more than that. There's my vector C. My resultant is this in your way?
Like a little bit to see C, but I can see it.
Periodic tables. All right. So the answer, all I've done is, in essence, is like putting this plus that plus that. I haven't actually come up with an answer yet. The answer is a vector from where I begin to where I end. That red arrow there is the answer. And apparently, I'm wanting to put this farther and farther out of in the corner so that we have more difficulty seeing it. Hopefully you can see it well enough.
Yeah.
Is there a way of actually shifting everything? No, not that way. It's one of these. Nope. Definitely not. I don't know what I'm doing. I think there's a way to move the whole thing, but I could be imagining that. Genesis?
So your resultant, that is, wouldn't the arrow be facing up, or does it matter?
Oh, it does. It does. If I push on the box like that, the net force is in that direction. If you throw the arrow in the other direction, you'd be saying, oh, the net force is that way. It's not. So it's from where you begin to where you end. It's if I had to give you just one vector to answer what is the sum, well, you have to start in the same spot and end in the same spot. So I started here, I ended there, that's what my vector is.
So a question like that, it would just be saying like, what is the sum of the vectors?
Yes. Or in math speak, because of course we don't want to use the same word more than once, the resultant.